This is Investigation 56, Graphing Rationals. We're going to be reminded today about our inverse variation functions, which are functions of 1 over x. So as a reminder, those functions have two asymptotes, a vertical asymptote, which is going to be along the y-axis, and a horizontal asymptote along the x-axis. The equations of those asymptotes are that the vertical asymptote has the equation of x equals 0, and the horizontal asymptote has the equation y equals 0. If we plot some points along those asymptotes, we plot points in quadrant 1, 1, 1, 2, 1/2, 3, 1/3, etc. And our graph in quadrant 3 would be at -1, -1, and then go along the x and y axis respectively. So that was our parent function for 1 over x. If you recall, we did some transformations on that where we would shift along a vertical and horizontal direction depending on where the location of that transformation was happening. This denominator of x minus 2 in the bottom means that that's going to be a horizontal move to the right. So that's going to take our vertical asymptote that used to be here at 0 and move it over 2 to the right to be at x equals 2. The plus 3, which is happening on the outside of our original function, is going to result in us moving the horizontal asymptote up 3 for a vertical transformation. The result is that our horizontal asymptote equation is y equals 3. So the graph itself is going to be in the same relative location to the axes, only the axes have moved 2 to the right and up 3 and created a new relative origin for where we're making our graph be located. All of that information is stuff we have covered before. We're now going to look at what if we wrote this equation using a common denominator so that we could write it as a single fraction. So to do that, we'd have to look and decide that the denominator is going to be x minus 2. And to create that common denominator of x minus 2, we'll multiply both the top and bottom of the second term, the constant 3, by x minus 2. The resulting numerator will be 1 plus 3 times the quantity x minus 2. We then need to do some simplifying in order to combine the like terms and distribute the top. And our final rewritten version of g of x would be that g of x is equal to 3x minus 5 over x minus 2. When we write our equation in this form as a polynomial divided by another polynomial, we call that a rational function. So a rational function is defined as a function that is a ratio or fraction of two polynomials such that the degree of the denominator is at least 1. In other words, we don't just want a constant under here. We want some type of a polynomial with a variable in it. And we're going to look at these functions presented this way now in our future study of our polynomial and rational function. As you turn to the back page, you'll see this function is actually given to us in factored form. So we can see that the different factors in the top and the bottom, if we were to multiply them out, we would see the two polynomials that make this be considered a rational function. When we look at the characteristics of this graph, we'll notice a few interesting things that are happening. One is that it has a vertical asymptote located here at x equals 3. It also appears to have a horizontal asymptote located here at y equals 2. There is a hole in this graph, as we can see clearly marked here, at the point 4, 3. And that is a unique situation that we have not encountered before, having a hole in the graph. We're going to look at how that affects then our domain and our range. The domain of the graph, remember, is all the x values that are used to make this graph exist. And as we can notice, there is no x value of 3 being used because that is the location of a vertical asymptote. And in addition, there's no x value of 4 being used because that is the location of the hole. In set notation, we would then write that the domain is all the x values except for 3 and 4, again, because of the vertical asymptote and the location of the hole. In a similar manner, when we go to look at the range, we're looking at which y values are used in this graph. And all the y values that are used, we're going fine all the way up to here. And then we reach this horizontal asymptote of 2, where we do not have y equals 2 being used in this picture. And similarly, where there's the hole, we do not have a y value of 3 because that point has been left out of this particular graph. And in set notation, again, we would then write y, all the y's, such that y does not equal 2 or 3 would be the values for our range. As we look at our equation and try to make some connections between the values and the characteristics we've seen here and where are they located up in this equation, you'll notice that we'll have excluded values of h of x, meaning they're the values that make the denominator equal 0. And so those values that make the denominator equal to 0, if we take a look here, this value, this factor would equal 0 if x were the value of 3. And this factor would equal 0 if x were the value of 4. So the excluded values are 3 and 4. And if we look at the domain and its relationship to those excluded values, those are in fact the exact same numbers. So the domain is representing the excluded values of the polynomial. We would say the domain contains all the x values except these excluded values. And at each of those excluded values, what we have happening is a discontinuity. At the asymptote, we have an infinite discontinuity, and at the hole, we have a point or removable discontinuity. So those discontinuities are the places, remember, where we have asymptotes or holes, and how are they related to those excluded values is that those excluded values themselves actually identify the locations of those discontinuities. Remember that removable discontinuities are the ones that are called point discontinuities. And if we look at where they happen when we look at our equation, we'll see that that happens at the factor that would in fact be able to algebraically reduce out, and that is what causes the hole. So it is the factor that could reduce out that causes the location for a removable or point discontinuity. The other denominator value of x equals 3 would be where we found the non-removable or infinite discontinuity. And so again, algebraically, those would be the factors that would be left after you've reduced everything that's possible. Any other factor in the denominator would give us an indication of an infinite discontinuity or non-removable. Jump discontinuities typically happen when we have something called a piecewise function, and our rational functions are not going to include the study of those at this time. In summary here, we have where we're going to find holes and vertical asymptotes. So I'm going to invite you to read through this as I pause the video here. Go ahead and pause it while you take a read through and see that you can identify the two vocabulary words here that would fill in these blanks. Hopefully you were able to come up with point or removable discontinuities are where we would find holes, and again that comes from the factors that reduce out. And vertical asymptotes would be infinite or non-removable discontinuities, and again those would be locations where the factor cannot be reduced. Some more vocabulary for you. I'll give you a second. Go ahead and pause the video here so that you can read through domain and range. And finally, 0 is a very powerful number that we want to make sure we don't make light of. Remember that when you have a number over 0, so there's a 0 in the denominator of that fraction, we are going to have some type of discontinuity in the graph. However, when we have 0 in the numerator of a fraction, that simply gives us an entire value of 0, and therefore that's actually just the location of the x-intercept, or a 0 of the function. And finally, remember, if you plug 0 in to your function, that's going to be giving you the location of this point, 0, comma y, which we should know represents the y-intercept. Go ahead and take a read on the description of intercepts, just as a reminder of what you should know from your past experience. Go ahead and pause the video and read through those descriptions. And now we're going to go ahead and apply all of this information to this example. You will notice this is already in factored form, and so if it was not in factored form, that is something that you would have to be able to do in the first place to get started. So remember to look for the vertical asymptotes. We're looking for the places where our graph has infinite discontinuities, and so we're going to find those by looking in our denominator. Now remember, if there is a factor that reduces, that's going to be a whole, and if it's a factor that does not reduce, that's going to be a vertical asymptote. So the vertical asymptotes will be located at x equals 2 and x equals -5, and this factor that would reduce, the x plus 3 factor, gives us the x value of our whole, that x would be located at -3, but we're going to need to find the value of y that goes along with that. So in order to find the value that goes with this x coordinate of -3, you're going to replace every x that's left with the value -3. Go ahead and substitute that in and see that you get the same answer I do. Hopefully when you've substituted in -3, you found a y value of +2, so the location of the whole is -3, 2. To find the x-intercept, that's where we're going to be looking for where the numerator will equal 1. Where the numerator will equal 0, and that value, of course, as we look up here in the numerator, is that x equals 1. So the x-intercept is located at 1, 0. And the y-intercept, this is where we say we plug 0 in for x in each of these. So the same exercise we used here, only use the value of 0 for x. And as you substitute 0 in to find our y-intercept, we should find the value of 1/2, and so the y-intercept would be at 0, 1/2. So when we look graphically to confirm all these characteristics that we just got by looking at the equation, we would want to just confirm that we see vertical asymptotes located here in the graph at both 2 and -5. We'd want to make sure that we see the coordinates of a whole located here at -3, 2. We're going to look for an x-intercept located here at 1, 0. And then we're going to look for our y-intercept to be located at 0, 1/2, which is about here. So we have in fact verified all of those characteristics in this picture that we've been given. We can further see the location of the horizontal asymptote at y equals 0, located at the x-axis. We can also then look to see the domain. Where, as I travel from left to right, do I end up not using values for x? So remember that the domain is connected to both the vertical asymptotes and any holes in the graph. So our domain is going to be all the values of x except -5, -3, and 2. For the range, we can go through a similar exercise. We're going up, up, and away with the exception of this value here at 0. However, If we look, this is only skipped out on the ends on the left side and the right side, but this value is used here for my x-intercept. So the range, while it looks like it skips the value of 0, actually contains the value of 0 here. And if we look closely, the same thing will happen here with our hole. While the value of 2 is not used at this location, the value of 2 is ultimately used here, and therefore is part of the range. So the range of this is actually that y is all the real numbers, and so we would write it here in set notation, all the y such that y is a member of all the real numbers. We do have some discontinuities to worry about. We have 2 infinite discontinuities and 1 point discontinuity. The infinite discontinuities happen at our vertical asymptotes, so that would be at x equals -5 and x equals 2. And our point discontinuity happens here at x equals -3. So that concludes our investigation on graphing rationals. We'll be doing a second investigation that builds on this with the next lesson. And so good luck on your practice, and bring any questions you have to Teams to ask for help.